Hello friends, I welcome you all to this class. This is linear algebra class, and today we want to solve this example under this topic, diagonalizable matrices. Now we say that a particular square matrix A is diagonalizable if you can find an invertible square matrix P and a diagonal matrix D such that diagonal matrix D will be equal to P inverse AP. So if you can find this invertible square matrix P such that the inverse of P multiplied by the given matrix square matrix A multiplied by P will give a diagonal matrix D, then that given square matrix A will be said to be diagonalizable. So we say that in our previous video we said that if the eigenvalues of that given matrix square matrix A are distinct, if the eigenvalues are distinct, then the matrix A will be diagonalizable. Then in this question, they ask us to determine whether the matrix A is diagonalizable or not. If it is diagonalizable, then we should find the diagonal matrix D. So for us to know whether this matrix is diagonalizable, we have to compute the eigenvalues. If the eigenvalues are distinct, no need of wasting time, it will be diagonalizable. If the eigenvalues are not distinct, then no conclusion yet. We need to compute the corresponding eigenvectors. If the eigenvectors are linearly independent, then the matrix will be diagonalizable. If the eigenvectors are not linearly independent, then the matrix will not be diagonalizable. So let's see how we can solve this question. Solution. Now to find the eigenvalues, you have to solve this equation, determinant of A minus lambda I, and equate it to 0. So this implies determinant of your matrix A, you have it on the board here. So this is what we have. Then minus lambda is a scalar, and your I is the n by n identity matrix. Since your matrix A is 3 by 3, this identity matrix will also be 3 by 3 identity matrix. So this will be the identity matrix. So this implies determinant of, to write our matrix A first, minus, let's use this lambda to multiply the identity matrix. So lambda multiplied by 1 is lambda, lambda multiplied by 0 is 0, lambda multiplied by 0 is 0, lambda multiplied by 0 is 0, lambda multiplied by 1 is lambda, lambda multiplied by 0 is 0, lambda multiplied by 0 is 0, lambda multiplied by 0 is 0, lambda multiplied by 1 is lambda. So determinant equated to 0. So this implies determinant of, let's subtract 1 minus lambda, 1 minus lambda, negative 1 minus 0 is negative 1, 3 minus 0 is 3, 0 minus 0 is 0, 1 minus lambda, we have 1 minus lambda, 0 minus 0 is 0, 0 minus 0 is 0, 0 minus 0 is 0, then 2 minus lambda, we have 2 minus lambda. So this is what we have, determinant equated to 0. So with this we have an upper triangular matrix. An upper triangular matrix, in an upper triangular matrix, from the principal diagonal, that is after the principal diagonal, the entries up, you should get at least one non-zero number. So we have non-zero numbers after the principal diagonal up, but below the principal diagonal you have what? Zeros. So we have 0, 0, 0. This is an upper triangular matrix. So to find the determinant of it, you multiply the entries of the principal diagonal. So this simply implies 1 minus lambda, 1 minus lambda, 2 minus lambda equals to 0. Multiply the entries of the principal diagonal. So this is already in factorized form. So this implies that what? That 1 minus lambda equals 0, or that 2 minus lambda equals what? 0. This because the product of this quantity are given us 0. Is either that because this and this are the same thing. So it's either that 1 minus lambda is 0 or 2 minus lambda is 0. So this implies that lambda, if you move negative lambda to the right, you have that lambda equals 1. or move negative 1, if you come here, move negative lambda to the right, you have that lambda equals was 2. So the eigenvalues are 1, 1, 2. So we're having 1, this is actually, the lambda equals 1 will be 1 twice, right? Because we have the same bracket here. So these are the eigenvalues. So we have 1, there will be 2, then, lambda equals 2, so and 2. This is what we have. Then we are going to get the corresponding eigen vectors. But the major work here is just this one that repeated twice. Remember, I told you that if the eigenvalues are distinct, then the matrix will be diagonalizable. But we have two eigenvalues which are not distinct. This one, the first lambda and the second lambda. So lambda 1 and lambda 2 are the same thing. So they are 1, 1. So if we get the eigenvector and the eigenvector are 2, corresponding to each of these one, lambda 1 and lambda 2. So the matrix will be diagonalizable. We don't need to check for the second, for lambda equals 2, because if you get this one to be distinct, if you get two eigenvectors for this and this, then this lambda 2 will surely give us an eigenvector. So we are going to have 3 linearly independent eigenvectors, which is what we are going to, which is what we are looking for it to be diagonalizable. Then if the eigenvectors corresponding to this repeated one, if they are not 2, then it will not be diagonalizable. So let's solve for the eigenvector corresponding to lambda equals 1, we solve this equation multiplied by capital X equated to 0. This is the general equation you are going to use to find the eigenvectors. A minus lambda I multiplied by capital X equated to 0. This capital X is the eigenvector you are looking for, and 0 is the zero matrix. So this simply implies since the lambda here is 1 multiplied by the identity matrix is identity matrix. So we have identity matrix. Then the X and the 0 we have here. So let's substitute. So this simply implies so our matrix A, we have it, let's write, minus the identity matrix 3 by 3 identity matrix. Your matrix A is 3 by 3. Then the capital X is a column vector you are looking for. Have entry x1, x2, x3. Because your matrix A is 3 by 3, it will have x1, x2, x3 as the entries. If your matrix A is 2 by 2, it will have x1 and x2. So equated to the column 0 matrix. So the next one we are going to have is, if you subtract, let's subtract 1 minus 1 is 0, negative 1 minus 0 is negative 1, 2 minus 0 is 2, 0 minus 0 is 0, 1 minus 1 is 0, 0 minus 0 is 0, 0 minus 0, 0, 0 minus 0, 0, 2 minus 1 is 1. So we have multiplied by the column vector, then equated to the 0 matrix. So this is what we have. So the next thing we are going to do is to reduce. We are going to reduce this matrix. So let's reduce it. We reduce this matrix. Now, the matrix will have So we reduce it by performing a roll operation on it. So let's perform a roll operation on it. Notice that row 2 have 0 throughout. If you are performing roll operation on a matrix, the one that has 0 throughout should not be at the middle, unless this last row, which is the row 3, which comes after row 2, are also 0. Unless this is 0 and this is 0. Basically, what I mean is that the row with the 0 entries throughout should be at the bottom. So since this row that has 0 throughout is at the middle, so we want it to be at the last. So we are going to interchange row 2 and row 3. So this is what I'm going to do. We are interchanging row 2 and row 3. So let's do that. And another one is that this row 1, the first non-zero number here is what? -1. I want it to be +1. So for simplicity's sake, I want it to be +1. So I'm going to do row 1 multiplied by -1. So let's carry this operation first. Multiply this row 1 by -1. We are going to have -1 multiplied by 0 is 0, -1 multiplied by -1 +1, -1 multiplied by +2 is -2. Then this operation is saying interchange row 2 and row 3. So let's interchange. So row 3 will come to row 2, and row 2 will come to row 3. So I've interchanged it, right? And we are done with the operation. We are done with the operation of this matrix. So we have so we are going to replace this matrix with this one we have gotten. So let's do that. So let's replace it. Equated to the 0 matrix. So this is, I'll replace this. I've replaced this with this. So this is what we now have. So after that, what is the next thing we're going to do? We are going to check whether each column has a leading entry of a row. Leading entry is just the first non-zero number in that row. If you come to row 1, what is the leading entry of row 1? The first non-zero number is 1. It's located where? It's located at column 2, right? So column 2 has a leading entry. You know x1 is for column 1, while x2 is for column 2. So the one that has a leading entry cannot be a free variable. So x2 cannot be a free variable. Come to column 3. What is we check whether it has a leading entry. Now, the first non-zero number in row 2 is located at column 3. So column 3 has a leading entry. So x3 cannot be a free variable. Column 1 does not have a leading entry of any row. Because of that, this x1 will be a free variable because x1 corresponds to what? Column 1. So let x1 be equal to alpha, element of real number. So we are going to say this is what? Free variable. So this is what we are going to have. So then we are going to solve this equation. Start from the last row. X1 multiplied by 0 is 0, plus x2 multiplied by 0 is 0, plus x3 multiplied by 0 is 0. 0 plus 0 plus 0. We are going to have 0 equated to 0. So no value for x1 and x3. So go to row 2. x1 multiplied by 0 is 0. x2 multiplied by 0 is 0. x3 multiplied by 1 is x3. So we are going to have x3. You'll be having x3 equal to what? 0. Right? You have x3 equals 0. So let's go to the first row, row 1. Let's go to row 1. So let's do the multiplication. x1 multiplied by 0 is 0, plus x2 multiplied by 1 is x2. x3 multiplied by -2 is -2x3. x3, right? Equal to what? 0. So if you make x to sort of the formula, it implies that was your x to be equal to move negative 2x3 to the right, you have positive 2x3, which is equals to 2 multiplied by 0, which is equals to 0. Because your x3 you have gotten is the x3 is 0. So x2 is also what? 0. So x2 is 0. So this with what I've gotten, so it implies that the column vector x having entry x1, x2, x3 will be equal to x1, we call it alpha, x2 is 0, x3 is 0. So alpha is just a real number. So you can choose any real number, preferably the simplest. So I can choose 1. Let alpha to be 1. So I have 1, 0, 0 at alpha equals what? 1. The matrix A is not diagonalizable. Is not diagonalizable since we got only one eigenvector corresponding to lambda 1 equals lambda 2. Which implies that the eigenvectors are not linearly independent. So this is the simple meaning of it. The eigenvectors are not linearly independent. We got only one eigenvector for two lambda. Lambda 1 is 1, lambda 2 is 1, and with only one eigenvector. So the eigenvectors corresponding to the lambdas are not linearly independent. So because of that, this matrix A will not be diagonalizable, because it is diagonalizable if the eigenvectors are what? Linearly independent. So the eigenvectors supposed to get two eigenvectors corresponding to as lambda 1 and lambda 2. So then after that, when you compute for lambda 3, you also get another eigenvector. So altogether you're supposed to get 3 linearly independent eigenvectors. So but for what, we only got one for lambda 1 and lambda 2. So if you do for lambda 3, you are going to get another one. So altogether you only get 2 eigenvectors instead of 3 linearly independent eigenvectors for each of the lambdas. So this matrix is not diagonalizable. So thank you so much for being part of this class. See you in the next class.